Hi everyone, welcome back to the TensorFlow channel. My name is Nikita and I'm a Google Cloud developer advocate focused on machine learning and data science. And today I'm going to walk you through a very friendly introduction to distributed training. I'll start by giving an overview of why distributed training is useful. Then we'll look at the differences between data parallelism and model parallelism, which are just two different ways of doing distributed training. Lastly, we'll dive into two different data parallelism algorithms, and I'll show you how to write this in code with TensorFlow. Now, before we get into the details, it's important to understand why we need distributed training in the first place. Deep learning works in part because of very large data sets. If your model training takes a few minutes or a few hours, you can quickly try out different ideas. If the training takes a few days, you can try out different ideas if you run some experiments in parallel. But if the training starts to take weeks, your progress will likely slow down as it's difficult to quickly experiment with new ideas. Using the right hardware configuration can dramatically reduce training time, and a shorter training time makes for faster iteration to reach your modeling goals. But distribution is not automatic. Even if your machine has 4 GPUs, like the one pictured here, if you don't make the necessary changes to your training code, your GPU utilization will be at 0% for all GPUs, except for one of them. And that's because TensorFlow can make use of a single GPU out of the box without any extra work on your part. But if you want to make use of more than one GPU, you'll need to do a bit of extra work. This extra work is necessary because TensorFlow needs to know how to coordinate the training process across the multiple GPUs in your runtime. But what does it even mean to distribute training? Well, there are two broad categories of algorithms: data parallelism and model parallelism. Generally, model parallelism works best for models where there are independent parts of computation that you can run in parallel. Data parallelism works with just about any model architecture, which makes it much more widely adopted for distributed training and a whole lot easier to get started with. The easiest way to understand data parallelism is just by thinking about the batch size. On each step of the model training, a batch of data is used to calculate gradients, which are then used to update the model's weights. Generally, the larger the batch size, the more accurate the gradients are. But we can only make the batch size so large before we start to run out of GPU memory. With data parallelism, we can add an additional GPU, which would allow us to double our batch size. In this case, each GPU gets a separate slice of the data, they calculate the gradients, and those gradients are averaged. So effectively, with 2 GPUs, your batch size becomes 64, and with 4 GPUs, it would become 128. This is the core idea in data parallelism. By adding more GPUs, your model is able to see more data on each training step, which means that it takes less time to finish an epoch, which is just a full pass through the training data. To understand this better, let's take a look at a diagram. We'll start with the linear model, and in TensorFlow, you can think of this model in terms of its computational graph. The matmul op takes in the X and W tensors, which are the training batch and the weights respectively. The resulting tensor is then passed to the add op with the tensor B, which is the model's bias terms. And the result of this op is Y-pred, which is the model's predictions. Note that this computation is basically equivalent to a dense layer with a single unit in Keras. So we want a way of executing this computational graph such that we can leverage multiple worker devices. And when I say a device, I just mean a CPU or an accelerator such as a GPU or TPU on some machine that TensorFlow can run operations on. Devices that are used to run computation are known as worker devices. And in this case, we have a single machine with 2 worker devices, which are both GPUs. With data parallelism, we distribute our dataset such that each worker device processes a different portion of the input batch on each training step with the same model. You can see an example in the diagram on the right. The input batch X is split in half, and one slice is sent to GPU 0 and the other to GPU 1. In this case, each GPU calculates the same ops, but on different slices of the data. So with 2 GPUs, you've effectively doubled your batch size. Now, another option would be to put different layers of your model on different machines or devices, and this is a type of model parallelism. You can see an example in the diagram on the right, where the matmul op is executed on GPU 0 and the add op is executed on GPU 1. In some cases, you might even do a combination of data parallelism and model parallelism, as shown in this image here. But remember, model parallelism works best for models where there are independent parts of computation that you can run in parallel. And this is usually best for advanced use cases, mostly in research. Data parallelism is definitely the easiest place for you to start, and it's almost always what you need. So for the rest of this talk, I'm just going to focus on data parallelism. But if you're curious to learn a little more about how model parallelism works, I've added a link to the Mesh TensorFlow library in the description box below, so feel free to check it out. Data parallelism algorithms can be synchronous or asynchronous, where synchronous or asynchronous refer to how the model parameters are updated. We'll take a look at what the differences are between synchronous and asynchronous algorithms in just a minute. But first, to make things more concrete, let's take a look at how you can add distribution to your TensorFlow code. Let's say you have a machine with 2 GPUs. You create your model using the sequential API, then compile and fit your model as usual. The actual details of the model here aren't super important. Now, when you call model.fit, TensorFlow will make use of one of the GPUs in your runtime automatically. If the dataset size is 768 and the batch size is 64, then on each step, our model sees 64 data points. That means a single epoch, which is just a full pass through the training data, takes 768 divided by 64 steps, which in this case is 12 steps. Now remember, in this scenario, we have 2 GPUs in our runtime, but we're only using one of them, and that's because we have not added any additional code to distribute our training. If we use both of them, we can double the batch size, cutting the steps per epoch in half. So let's see how we can update this code so we can make use of that second GPU. First, we need to define our distribution strategy. We do this using the TF Distribute Strategy API, which provides different distributed training strategies that you can easily incorporate into your program. In this example, we'll use the simplest strategy, mirrored strategy, which allows you to distribute training across multiple GPUs on a single machine. Next, we need to scale up the batch size by the number of GPUs. This is because the batch size now refers to the global batch size. In other words, if you pass a batch size of 64 and you have 2 GPUs, then each GPU will process 32 examples per step. In this case, 64 is known as the global batch size and 32 as the per replica batch size. And a replica is just a fancy way of saying a copy of the model running on one slice of the input data. So to make the most of your GPUs, you'll want to scale the batch size by the number of replicas, which in this case is 2 because we have 2 GPUs. Instead of hard coding the number of GPUs, you can use the num replicas in sync method, as you can see in the code here. Next, we'll wrap the creation of our model variables within the scope of our strategy. And this step is crucial because it tells mirrored strategy which variables to mirror across your GPUs. When we call model.fit, mirrored strategy will make a copy, known as a replica, of the model on both of the GPUs. And the CPU is responsible for preparing the TF data dataset batches and sending the data to the GPUs. And that's it. Those are all the changes you'll need to make to your code. So now that you know how simple it is to incorporate this strategy into your TensorFlow code, let's take a deeper dive into what's actually going on when we call model.fit. First, we return to our linear example from before. Remember, the input data X is split in 2 because we have 2 GPUs, and one slice of the data goes to GPU 0 and the other to GPU 1. Each GPU performs the forward pass on a different slice of the input data to compute the loss. Each GPU then computes the gradients based on the loss function. But we now have two sets of gradients, one that was computed by GPU 0 and the other that was computed by GPU 1. So we need some way of turning these two sets into one. And we're going to do this by averaging the gradients, and then using this averaged value to update our model parameters. Turning these two sets of gradients into one set of gradients happens at the end of each step. The optimizer then performs the parameter updates with the reduced gradients, thereby keeping all the devices in sync, hence the name Synchronous. Because each GPU can't proceed to the next training step until all other GPUs have finished the current step, this gradient calculation becomes the main overhead in distributed training for synchronous strategies. So even though this calculation is usually just a simple average, it needs to happen really efficiently. To put it simply, the less time the orange boxes take, the faster our model will train. In distributed training, we call this reduction from multiple sets of gradients to one set of gradients an all-reduce. And a more formal way of saying this is that an all-reduce is an operation that reduces a set of arrays on distributed workers to a single array that is then redistributed back to each worker. The diagram here shows 4 GPU workers. Before the all-reduce operation, each GPU has an array of gradients that were calculated on its batch of training data. So the A, B, C, D here just refer to the calculated gradients. And again, because each GPU received a different slice of the training data batch, the subsequent gradient arrays are all different. So A0 is different from A1, and so on. And we want to average these A values, average the B values, etc. So to take an average, we need to first sum the corresponding gradients for each parameter and then divide. The summation portion of this average is actually the tricky part, because each GPU needs to know the values of the gradients computed by all other GPUs. And we want to pass this information between the GPUs as efficiently as possible and use as little bandwidth as possible. So after the all-reduce operation is completed, each GPU will have the same array. And this array is computed by aggregating, which is a summation, the gradient arrays across all workers. And at this point, we could compute the average by taking a simple division. So the question is, how do we get from the top row of this diagram to the bottom row? How do we move all this data such that every GPU has every other GPU's gradients all added up? Well, there are many different algorithms for efficiently implementing this aggregation. The choice of the topology and the gradient exchange pattern all impact the bandwidth required by the algorithm and its latency. Note that TensorFlow will take care of selecting the algorithm and computing this aggregation for you. So you actually don't really need to know all the details, but if you're curious, I'm going to walk through an example of an all-reduce implementation called ring all-reduce, where the workers form a logical ring and communicate only with their immediate neighbors. There are 2 phases to this algorithm, the reduce scatter phase and the all gather phase. At the start of the reduce scatter phase, the gradient array on each GPU is divided into n equal size blocks, and n here refers to the number of GPUs, which in this case is 4. In the next step, each GPU simultaneously sends one of these gradient blocks to a neighbor and receives a different block from the other neighbor. GPU 0 sends A0 to GPU 1 to be added to A1. GPU 1 sends B1 to GPU 2, and GPU 2 sends C2 to GPU 3, and finally, GPU 3 sends D3 to GPU 0. These send and receive operations in the ring are all simultaneous. When the step completes, each GPU can perform a partial reduction, which again is a summation, using the block that it received from its neighbor. After the partial reduction, the GPUs exchange partially reduced blocks. GPU 1 sends the reduced A1 plus A0 to GPU 2. GPU 2 sends the reduced B2 plus B1 to GPU 3, and so on. One way to think about this is that the authoritative value for each block of gradients is just getting pushed around this ring. Now, at the end of the reduced scatter phase, each GPU will have one fully reduced block of the original arrays, which means that we now have an authoritative summed value for A, B, C, and D, but it's distributed all over the place. So we have to collect these values and make sure that every GPU ends up with the same array. At this point, the all-gather phase of the algorithm starts. GPU 0 sends the fully reduced B0 plus B3 plus B2 plus B1 to GPU 1. GPU 1 sends the fully reduced C1 plus C0 plus C3 plus C4 to GPU 2, and so on. At the end of the all-gather phase, all GPUs have the same fully reduced array. And at this point, each GPU can do a simple division operation to calculate the average gradients. Ring-all-reduce is just one way of efficiently communicating gradients across workers. And while it's not too difficult to understand, a downside of the ring-all-reduce algorithm is that the latency of the algorithm scales linearly with the number of workers. Other implementations of all-reduce based on tree topologies can actually achieve logarithmic scaling, while the latency for other algorithms, such as the GCP reduction server, don't actually depend on the number of workers. But again, you don't really need to worry about the underlying all-reduce implementation. TensorFlow is going to take care of that for you. What's more important to understand is the bigger picture of what happens when we wrap the creation of our model variables in the scope of mirrored strategy. Mirrored strategy will make a copy of the model on all of our GPUs. The CPU will prepare the TF data dataset batches and send them to the GPUs. Then, when we call model.fit, each GPU will perform the forward pass on a different slice of the input data to compute the loss. Each GPU computes the gradients based on the loss function. These gradients are aggregated across all of the devices via an all-reduce algorithm. The optimizer updates the weights using the reduced gradients, thereby keeping the devices in sync. Now, as I mentioned earlier, mirrored strategy is used when you have a single machine with multiple GPUs. But TensorFlow also has an equivalent strategy for when you want to take your distributed training to the next level and do synchronous data parallelism on multiple machines, each with potentially multiple GPUs. Now, while I'm not going to get into the details in this talk, this strategy is called multi-worker mirrored strategy. And it works pretty similarly to mirrored strategy, except that instead of just synchronizing the gradients across all GPUs on a machine, at the end of each step, the gradients need to be synchronized across all GPUs on a machine and all machines in the cluster. You can also use this strategy when you have a cluster of CPU-only machines, so it can be a good option if you don't have access to GPUs. In a multi-worker mirrored strategy setup, all of the machines in your cluster are designated as workers, which are the physical machines on which the replicated computation is executed. In addition to each machine being a worker, there will also be one worker that takes on some additional extra tasks, such as saving checkpoints and writing summary files to TensorBoard, and this machine is known as the chief. There are some additional implementation details to keep in mind when you use the strategy, such as how you save and dataset sharding, but those are out of scope for now. If you'd like to learn more, just check out the resources in the description box below. So far, we've discussed two synchronous distribution strategies in TensorFlow: mirrored strategy and multi-worker mirrored strategy. But data parallelism does not need to be synchronous. In asynchronous data parallelism, each worker also computes the gradients from a slice of the input data, but makes updates to the parameter in an asynchronous fashion. Compared to synchronous strategies, asynchronous training has the benefit of fault tolerance because the workers are not dependent on one another. Parameter server training is a common asynchronous data parallelism method to scale up model training on multiple machines. A parameter server training cluster consists of workers and parameter servers. And as the name suggests, your model's parameters are stored on the parameter servers. On the other hand, workers read and update these variables independently without synchronizing with each other. In TensorFlow, the parameter server architecture also includes a coordinator, which creates resources, dispatches training tasks, writes checkpoints, and deals with task failures. So how do these asynchronous updates work? Well, each worker independently fetches the latest parameter values from the parameter servers and computes the gradients based on a subset of training samples. Workers then send gradients back to the parameter servers, which update the parameters with those gradients. Each worker does this independently. Because the workers are not waiting for each other like they are when we do synchronous data parallelism, asynchronous training scales well to a larger number of workers, where your training workers might be preempted by high-priority production jobs, or maybe a machine goes down for maintenance. The downside of this approach is that workers can get out of sync, as they could be computing parameter updates based on stale values, which might delay convergence. So let's take a look at an example in code. Like the other strategies, you first need to instantiate your strategy object. Note that parameter server strategy should be used when you want to distribute training across multiple machines in a cluster. So it's essentially the asynchronous equivalent of multi-worker mirrored strategy. When you create the strategy object, you need to pass in something called a cluster resolver, which is just a simple configuration of the machines in your cluster. If you want to learn more about how this works, just check out the parameter server guide in the description box below. When you use parameter server strategy, it's recommended that you shuffle and repeat the data. And this is to help achieve better coverage of the input data because the strategy doesn't guarantee which worker runs a particular step. Next, we wrap the creation of the model variables within the scope of our strategy, and this step should look pretty familiar by now. We discussed earlier that in the mirrored strategies, a copy of the model is created on each of your GPU workers. But in parameter server strategy, the variables are stored on the parameter servers only. Workers do not store variables, they only perform the computation. Because we repeat the dataset, we need to pass the argument steps per epoch to model.fit. So let's say you had a cluster with one parameter server and 2 workers. If your steps per epoch was 10, then one epoch would be complete when 10 gradient updates have occurred. And note that these updates don't need to be balanced across the 2 workers. Because the strategy is asynchronous, it's entirely possible that each worker computes 5 gradient updates in the epoch, or that one of them does 6 while the other only does 4, etc. Again, I've left off some minor implementation details here, but if you want to learn more, just check out the link in the box below. Let's recap everything that we've seen today. So far, we've looked at 2 types of data parallelism algorithms, synchronous and asynchronous. When discussing synchronous training, we looked at 2 distribution strategies available in TensorFlow, mirrored strategy and multi-worker mirrored strategy. You can use mirrored strategy if you want to distribute training across multiple GPUs on a single machine. In this case, the variables are mirrored across the GPUs, meaning that a copy of your model is created on each GPU. Gradients are synchronized across the GPUs at the end of each step. You can use multi-worker mirrored strategy if you want to distribute training across multiple machines in a cluster, each with potentially multiple GPUs. In this case, the variables are mirrored across the GPUs, and at the end of each step, the gradients are synchronized across GPUs on a machine and all machines in a cluster. Lastly, we looked at parameter server strategy, which you can also use when you want to distribute training across multiple machines in a cluster. Variables are not mirrored across the workers. Instead, they're stored on parameter servers. Workers independently fetch the latest variables from the parameter servers, compute the forward and backward paths on a slice of the training data, and send the gradients back to the parameter servers in an asynchronous fashion. You now know the basics of distributed training with TensorFlow. To help you take your skills to the next level, I've recorded a short demo of how to use mirrored strategy with multiple GPUs on Google Cloud, and you can find this linked in the description box below. Thanks so much for watching, and happy distributed training!